Welcome! Today, we'll be solving LeetCode problem number 1093, Statistics from a Large Sample. This problem challenges us to compute 5 key statistical metrics: minimum, maximum, mean, median, and mode from a given frequency distribution. By the end of this session, you'll gain insights into handling large datasets and applying statistical computations efficiently. Let's dive in. In this problem, you are given a large sample of integers that are distributed within the range of 0 to 255. Your task is to compute 5 key statistics that describe this distribution. These include the minimum, which is the smallest integer in the dataset, and the maximum, which is the largest integer. You'll also need to calculate the mean, which is the average value of all the integers in the sample, and the median, which represents the middle value when the data is sorted. If the sample size is even, the median will be the average of the two middle values. Finally, you'll determine the mode, which is the integer that appears most frequently in the data. If there are multiple integers with the same highest frequency, you should return the smallest one among them. To make this process efficient, the input is given as an array called count, where the value at each index represents the number of times the corresponding integer appears in the sample. For example, count 3 tells you the frequency of the integer 3 in the dataset. The output for this problem is a list called result that contains the 5 statistics you've calculated. Specifically, result 0 will store the minimum value, result 1 will contain the maximum value, result 2 will hold the mean, result 3 will have the median, and result 4 will represent the mode. Let's look at an example to understand this better. Suppose you are given an input array count where the values are distributed as shown. The output for this input is 1, 3, 2.375, 2.5, 3. This means the smallest value in the sample is 1, the largest is 3, the mean is 2.375, the median is 2.5, and the mode is 3. These outputs are derived based on the rules for calculating each statistic, which we'll break down further. Here's how the values in the first example are calculated. The minimum is 1 because the frequency of 1 in the count array is greater than 0. Similarly, the maximum is 3 because count 3 is also greater than 0. The mean is determined by summing the product of each number and its frequency, and then dividing by the total sample size. For the given input, this calculation results in 2.375. The median is calculated by finding the middle value of the sorted data. In this case, the dataset has an even size, so the median is the average of the two middle numbers, which gives 2.5. Finally, the mode is 3 because it appears most frequently, with a count of 4. Now let's consider another example to reinforce this understanding. In the second example, the minimum value is 50, as it is the smallest integer with a non-zero frequency in the count array, and the maximum value is 52 for the same reason. The mean is calculated as the weighted average, which comes out to approximately 51.1667. The median is 51, as it is the middle value of the dataset. Finally, the mode is 52, since it appears most often with a frequency of 3. To solve this problem effectively, it's important to consider the constraints. For instance, the input array is always of size 256, and all frequency values are non-negative, with their sum being at least 1 and at most 10 to the power of 9. You'll also need to handle edge cases, such as when the sample contains only one unique integer or when precision is required for large frequencies. Implementing the solution efficiently while accounting for these scenarios is key to solving this problem correctly. To tackle this problem, we need to compute 5 key statistics: the minimum, maximum, mean, median, and mode, all derived from a frequency distribution of integers within the range of 0 to 255. The input, given as an array called count, represents the frequency of each integer in the sample. Let's first consider the brute force approach. This method involves reconstructing the entire dataset by iterating over the count array. For the minimum and maximum, we simply identify the first and last non-zero elements in the array. To calculate the mean, we sum up all the values and divide by the total count of elements. For the median, we rebuild the dataset, sort it, and locate the middle value or values. The mode is determined by finding the index with the highest frequency in count. While this approach is intuitive and straightforward to implement, it is computationally expensive. Reconstructing the dataset, especially when the frequencies are large, results in significant time and space complexity, making this method impractical for large-scale samples. A more efficient method is the optimized approach that leverages cumulative frequencies directly from the count array. By avoiding dataset reconstruction, we can compute the statistics in a more streamlined way. For the minimum and maximum, we traverse the count array to find the first and last non-zero indices. The mean is calculated as we traverse, accumulating the weighted sum of values using sum plus equals I asterisk count, I, and the total count using total plus equals count, I. The median is determined using cumulative frequencies to pinpoint the middle value or values, eliminating the need for sorting or reconstruction. For the mode, we identify the index with the maximum frequency by traversing the array. This approach is highly efficient, as the count array has a fixed size of 256, giving it a constant time complexity of 0.1. Additionally, an alternative method involves using prefix sums, which pre-computes cumulative sums in a separate array to simplify median calculation, although this slightly increases space usage. Another option is binary search for the median, which could be helpful for larger ranges but is unnecessary given the fixed range of 0 to 255. The chosen strategy for this problem is the optimized approach using cumulative frequencies. This method was selected because it strikes the right balance between efficiency and simplicity. By iterating over the count array only once, we can compute all required statistics without reconstructing the dataset, avoiding the inefficiencies of the brute force approach. There are several key observations that make this method particularly suitable. First, the fixed range of 0 to 255 allows us to treat the problem as having constant time complexity, or 0.1. Second, cumulative frequencies enable efficient median calculation without requiring additional sorting or reconstruction steps. Finally, the count array already provides all the necessary information for direct computation, making this approach both elegant and practical. In terms of efficiency, this method minimizes computational overhead, while its simplicity reduces the likelihood of implementation errors. Additionally, although the range in this problem is fixed, the method generalizes well to larger ranges with only minimal adjustments. Although this approach is optimal for the given constraints, there are some trade-offs to consider. For example, careful handling of edge cases, such as determining the median for even-sized samples, is required to ensure accuracy. While alternatives like binary search or prefix sums could simplify specific calculations, they would introduce unnecessary complexity given the fixed range of 0 to 255. The optimized cumulative frequency method strikes a balance by being efficient, straightforward, and scalable. It avoids the space and time pitfalls of brute force approaches while fully utilizing the structure of the count array. This makes it an excellent choice for solving this problem under the given constraints, ensuring that all statistics are computed accurately and efficiently without unnecessary overhead. To solve this problem, we need to compute 5 key statistics: minimum, maximum, mean, median, and mode, derived from a dataset represented as a frequency array. The input is an array named count, where each index represents an integer from 0 to 255, and the value at each index tells us how many times that integer appears in the dataset. For instance, if count 3 equals 7, it means the number 3 appears 7 times in the data. To efficiently compute these statistics, we need to initialize a few variables. Min_val and max_val will help us track the smallest and largest integers with non-zero frequencies. Total_sum will store the sum of all integers in the dataset, while total_count will represent the total number of elements. Finally, we need to track the mode, which is the integer appearing most frequently, using an additional variable max_frequency to monitor the highest frequency encountered. These variables are essential because they allow us to extract multiple statistics in a single pass through the data. Now, we perform the first traversal of the count array. This step is crucial for gathering most of the required statistics. As we iterate through integers from 0 to 255, we check if the frequency at each index, count I, is greater than 0. If it is, we know the integer I exists in the dataset. During this traversal, the min_val gets updated as soon as we encounter the first non-zero frequency. Since we're scanning from left to right, this ensures min_val is set to the smallest integer present. Similarly, max_val gets updated to I whenever we find a non-zero frequency, so by the end of the loop, it holds the largest integer in the dataset. For total_sum, we add the value I*count, I, to capture the contribution of integer I to the dataset's total sum. Similarly, we increment total_count by count, I, which keeps track of the total number of elements. Finally, we compare count, I, with max_frequency to determine if the current integer I should become the new mode. This single pass efficiently collects the min, max, mean, and mode. Once the pass is complete, we calculate the mean using the formula mean equals total_sum/total_count, since we now have both total_sum and total_count ready. After computing the mean, we move on to calculating the median. To do this, we need to identify the middle value, or values, in the dataset when sorted. This requires a second traversal of the count array. We start by initializing a cumulative_count variable to 0. This variable keeps a running sum of frequencies as we traverse. The idea is to determine when cumulative_count reaches or exceeds half the total count of the dataset, represented by total_count/2. For datasets with an odd total count, the median is simply the integer at this position. For even-sized datasets, we need to average the two middle elements. This is done by carefully tracking the transition when cumulative_count crosses the halfway point. Using this cumulative approach, we can efficiently locate the middle values in 256 time, which is constant due to the fixed size of the count array. Once the median is identified, we return all the computed statistics min_val, max_val, mean, median, and mode as the final result. This algorithm leverages the fixed size of the frequency array to achieve remarkable efficiency. Since the input array always has 256 elements, the time complexity is 256, or simply 1. Most statistics, min, max, mean, and mode, are gathered in a single pass, while the median computation requires a second pass. This two-pass approach ensures we only traverse the array twice, making it computationally inexpensive. The cumulative count technique is particularly effective for finding the median, as it avoids the need to sort the dataset explicitly. Instead, we locate the middle elements by progressively summing the frequencies. In terms of data structures, the frequency array itself is central to the solution, providing constant time access to any numbers count. Additionally, we use a few auxiliary variables like min_val, max_val, total_sum, and total_count to track key statistics during traversal. Importantly, the space complexity remains 1, since we only use a fixed amount of extra space regardless of the dataset size. This combination of efficiency and simplicity makes the algorithm highly scalable. Finally, it's important to consider edge cases to ensure the algorithm handles all possible inputs robustly. For instance, if the count array contains only zeros, this indicates an empty dataset. In such cases, the algorithm should return default values for all statistics. For a dataset with only a single element, the min, max, mean, and median should all equal that element, and the mode should also reflect it. Another key consideration is the difference between even and odd dataset sizes when calculating the median. For odd-sized datasets, the median is the middle value, while for even-sized datasets, it's the average of the two middle values. The algorithm handles both scenarios seamlessly by examining the cumulative count during the median computation. By addressing these edge cases, we ensure the solution is robust and reliable for any input configuration. Here, we begin with the definition of the sample stats function, which takes a list called count as its input. This list contains the frequency of integers ranging from 0 to 255. The first step is to calculate the total number of elements in the dataset, stored in the variable n. Next, we find the smallest and largest values in the dataset that have a non-zero frequency. The min_val is determined by iterating from 0 to 255 and identifying the first value with a count greater than 0. Similarly, the max_val is determined by iterating in reverse, from 255 to 0, to locate the last non-zero value. Now, to compute the mean, we calculate the weighted sum of all values by multiplying each integer by its frequency and summing them up, stored in total_sum. Dividing this sum by the total number of elements gives us the mean. After that, we focus on calculating the median. The median depends on whether the total count of elements is odd or even. First, we determine the middle index, mid, and initialize cumulative underscore count to 0. If the total number of elements is odd, we iterate through the dataset, adding frequencies to the cumulative count until it exceeds mid. When this condition is met, the corresponding value becomes our median. When the total number of elements is even, the median is the average of the two middle values. In this case, we continue iterating through the dataset, updating the cumulative underscore count. The variable left is assigned the first middle value when the cumulative count surpasses mid 1, and right is assigned the second middle value when the cumulative count exceeds mid. Once we have both left and right, the median is calculated as their average. Next, we compute the mode, which is the value with the highest frequency. Using Python's max function with a lambda expression, we identify the index in the count array that corresponds to the maximum frequency. Finally, the function returns a list containing the 5 statistical metrics: the minimum value, the maximum value, the mean, the median, and the mode. This comprehensive output provides a clear summary of the statistical properties of the dataset. Here, we begin by defining the sample stats method, which takes in an array count representing the frequency of integers from 0 to 255 in the dataset. First, we initialize several variables. The n variable will store the total number of elements in the dataset, while minval and maxval will track the smallest and largest values respectively. We also set up variables for the mean, median, and mode, as well as maxCount to track the frequency of the mode. Additionally, total sum is initialized to calculate the sum of all values, which will be used later for computing the mean. Now, we enter a loop that iterates over all 256 possible values in the dataset. For each value, if its frequency in the count array is greater than 0, we update the minval if it hasn't been set yet, and update maxval to reflect the highest value seen so far. We also calculate the contribution of this value to the total sum and increment the total count n. Finally, we check if the current value has the highest frequency so far to update the mode. This loop ensures that we collect all the necessary statistical data such as the total count, minimum, maximum, mean, and mode. Next, we calculate the median. To begin, we determine the midpoint of the dataset, which is n/2. Then, we initialize cumulative count to track the running total of frequencies as we iterate through the values, and two variables, left and right, to help calculate the median in the case of an even number of elements. As we loop through the dataset again, we add each value's frequency to cumulative count. For datasets with an odd total count, when cumulative count exceeds the midpoint, we know we've found the middle value, and we assign it to the median. For even datasets, we need to find two middle values. The first middle value is identified when cumulative count exceeds mid 1, and the second middle value is found when cumulative count exceeds mid. Once both values are identified, the median is calculated as their average. This approach ensures that the median is accurately computed for both odd and even datasets. Finally, we return an array containing all the calculated statistics: the minimum, maximum, mean, median, and mode. The implementation concludes with the closing braces for the class and method definitions. With this structure, the solution is cleanly encapsulated within the solution class, making it easy to test and reuse. The samplestats method processes the input frequency data efficiently in 256 time due to the fixed iteration range, ensuring excellent performance regardless of the dataset size. This method provides a complete statistical summary of the data, including the minimum value, maximum value, mean, median, and mode. To begin, we have a simple input where only indices 1 and 2 have non-zero counts, specifically 2 and 3 respectively. First, we calculate the total number of elements by summing all the counts, which gives us 5. This represents the total number of data points in the distribution. Next, we determine the minimum value by identifying the smallest index with a non-zero count, which is 1 in this case. Similarly, we find the maximum value by identifying the largest index with a non-zero count, which is 2 here. Moving on to the mean, we calculate the weighted sum of all indices, where each index is multiplied by its respective count. This gives us a total sum of 8, and dividing by the total number of elements, 5, results in a mean of 1.6. Now, we compute the median. Since the total number of elements, n, is 5, which is odd, the median corresponds to the middle element of the dataset, or the third element. We traverse the cumulative frequencies, keeping track of how many elements we've encountered. Once the cumulative count exceeds the midpoint, which is 2, the median is identified as the current index, which is 2. For the mode, we look for the index with the highest count. Here, index 2 has the highest count of 3, so the mode is 2. The final output for this example is an array consisting of the minimum value, maximum value, mean, median, and mode 1, 2, 1.6, 2, 2. In this example, we analyze an edge case with a uniform distribution. The count array has equal frequencies of 1 for indices 0 through 4, while the rest are zeros. First, we calculate the total number of elements, which is simply the sum of all counts. Here, it equals 5. The minimum value is determined by finding the smallest index with a non-zero count, which is 0. The maximum value, meanwhile, is the largest index with a non-zero count, which is 4. These values represent the range of the dataset. Next, we calculate the mean by taking the weighted sum of all indices and dividing by the total number of elements. For this input, the total sum is 10, resulting in a mean of 2.0. To find the median, we note that n is odd, so the median corresponds to the third element. As we traverse the cumulative frequencies, we identify the index where the cumulative count exceeds the midpoint, which is 2. Thus, the median is also 2. For the mode, since all frequencies are equal, we select the smallest index with the maximum frequency, which is 0. This ensures consistency when handling ties. The final output for this example is 0, 4, 2.0, 2, 0. Finally, let's consider a sparse and skewed distribution. Here, the count array has a single non-zero value of 10 at index 100, representing a highly concentrated dataset. First, the total number of elements is calculated as 10. The minimum value is determined as the smallest index with a non-zero count, which is 100. Similarly, the maximum value is the largest index with a non-zero count, which is also 100. This highlights that all the data points are concentrated at a single value, making the range effectively 0. The mean for this distribution is straightforward to compute. Since all 10 data points are at index 100, the total sum is 1000, and dividing by the total number of elements gives a mean of 100.0. For the median, since n is even, the median is the average of the fifth and sixth elements. As we traverse the cumulative frequencies, we identify that both the fifth and sixth elements fall at index 100. Thus, the median is calculated as the average of these two indices, which is 100.0. This reinforces the concentrated nature of the data. Finally, the mode is determined as the index with the highest count. Here, index 100 has a count of 10, making it the mode. The final output for this example is 100, 100, 100.0, 100.0, 100. This demonstrates how the solution handles skewed distributions effectively. Overall, this approach systematically calculates each statistic, minimum, maximum, mean, median, and mode, through efficient traversals and aggregation. The examples showcase its versatility across simple, uniform, and highly skewed distributions, ensuring robust performance across various input scenarios. In this solution, we begin by analyzing the time complexity of each operation. First, calculating n, which is the total number of elements, involves summing up all the values in the count array. Since this array always has a fixed size of 256, the operation sum, count, iterates over all its elements. Regardless of the input values, this sum operation is constant in time, hence the complexity is O, 256, which simplifies to O, 1. Next, finding the smallest non-zero value, min_val, involves searching through the count array for the first index with a non-zero value. Even in the worst case, where all values are 0 except for the last element, this search will always terminate after 256 iterations, which is again constant time, O, 1. Similarly, finding max_val, the largest non-zero value, requires iterating in reverse through the array. The logic is the same, a maximum of 256 iterations results in a time complexity of O, 1. These operations are efficient because the size of the array is fixed and independent of the input data's scale. Now, let's analyze the time complexity of calculating the mean. This operation involves iterating through all 256 indices, multiplying each index by its corresponding count, and summing up the results. Since this is a single pass through the fixed-size array with constant operations at each step, the time complexity remains O1. For the median, we need to traverse the count array while maintaining a cumulative sum until we locate the middle index. In the odd case, we stop as soon as the cumulative count surpasses n//2. In the even case, we track two middle values if necessary, but this still requires just one pass through the array. Again, because the array has a constant size, this operation is O1. Lastly, determining the mode involves scanning through the array to find the index with the highest count. This operation iterates over all 256 indices, comparing values, and is therefore constant in time, O1. These computations demonstrate the efficiency of directly working with the fixed-size count array. When we consider all these individual operations together, the total time complexity of the solution remains O1. Each operation, whether it's calculating n, finding min_val or max_val, or calculating statistical measures like the mean, median, and mode, is bounded by a constant number of iterations due to the fixed size of the count array. Now, looking at space complexity, the input count array is part of the input data itself and does not contribute to additional space usage. For auxiliary space, the algorithm uses only a constant amount of memory for variables like n, min_val, max_val, and others. Since no additional data structures are created and all operations are performed in place, the space complexity is O1. This holds true across all scenarios: best, average, and worst case, since the size of the count array is always fixed at 256. To put this into perspective, let's compare this optimized solution with a brute force approach. The naive method would involve reconstructing the dataset by expanding the count array into its actual values. For instance, if count I equals 3, the value I would appear 3 times in the dataset. This reconstruction requires O(n) time and space, where n is the sum of all elements in count. Performing statistical calculations on this reconstructed dataset would add further overhead, making the brute force approach highly inefficient with a complexity of O(n). In contrast, the optimized solution avoids this reconstruction entirely by directly operating on the fixed-size count array. This results in constant time and space complexity, O1. Mathematically, the algorithm performs a fixed number of iterations across all operations, independent of the input size, confirming that the time complexity is O1. Similarly, as no new data structures are created, the space complexity remains O1, making this solution both elegant and efficient. When solving this problem, there are some common mistakes to watch out for. First, ignoring edge cases like empty or uniform frequency distributions can lead to serious errors. For example, if all integers have zero frequency, or only one value has a non-zero frequency, you might encounter division by zero issues or incorrect results for mean, median, and mode. Next, the median calculation can go wrong if you don't handle even frequencies correctly. When the total count is even, the median is the average of the two middle values, which requires precise tracking of cumulative frequencies. Lastly, precision errors in mean calculation are another frequent pitfall. If you use integer division instead of floating point division, you risk truncation errors, especially with large total frequencies. Handling these scenarios properly is critical for accurate outputs. Another set of mistakes stems from inefficient approaches to computations. For instance, repeatedly iterating through all 256 possible values to find the mode is unnecessary and can significantly increase time complexity. Instead, the mode can be determined more efficiently in a single pass while updating frequencies. Similarly, failing to optimize for sparse frequency distributions can waste computational resources. If most frequencies are zero, always iterating over all 256 values becomes redundant. By skipping zero frequency values, especially in sparse inputs, you can reduce the overall number of operations and make the solution much faster. These optimizations are key to writing efficient and scalable code. This problem also offers valuable interview insights. One of the key patterns it tests is your ability to work with cumulative frequency distributions and simulate statistical calculations efficiently. Mastering this pattern can help you solve other problems involving prefix sums or cumulative statistics. Additionally, interviewers often look for optimization skills, so while a brute force approach might work, they expect solutions that are optimized for sparse distributions and handle multiple statistics in a single traversal. Precision handling is another focus area, as floating point accuracy is critical for mean and median calculations. Preparing to explain how you address edge cases and rounding errors is crucial. Lastly, structuring your solution into modular steps, such as separating cumulative frequency calculations from statistical computations, demonstrates strong coding practices and clarity in your approach. There are also related problems that can help reinforce the concepts in this challenge. For example, LeetCode 295, Find Median from DataStream, focuses on dynamically calculating the median as new integers are added, which directly builds on median-related logic. LeetCode 528, Random Pick with Weight, emphasizes cumulative frequency distributions and prefix sums, which are central to this problem. LeetCode 1346, Check if n and its double exist, highlights efficient traversal and frequency tracking techniques. Finally, LeetCode 1010, Pairs of songs with total durations divisible by 60, demonstrates frequency-based optimizations in a different context. Exploring these problems can deepen your understanding of frequency-based algorithms and help you recognize patterns across various challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. The two-pass method involves using one pass to calculate cumulative frequencies and a second pass to compute the required statistics. While this approach is straightforward and easy to implement, it's less efficient than a single traversal. On the other hand, the single-pass optimized approach combines the calculations for all statistics such as the minimum, maximum, mean, median, and mode into a single traversal. This is more efficient but requires careful implementation to avoid errors. Additionally, for sparse frequency distributions, using a dictionary or a sparse array allows you to skip zero frequency values. This optimization is particularly useful for sparse inputs, as it significantly reduces computation time, though it may slightly increase memory usage. Choosing the right approach depends on the constraints and requirements of the problem at hand. Great job! To wrap up, we successfully solved LeetCode problem number 1093 by computing key statistical metrics from a frequency distribution. This problem highlighted the importance of efficient data handling and algorithmic thinking. Remember to revisit these concepts and practice similar problems to strengthen your skills further. Thanks for watching. Don't forget to like, subscribe, and join us for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!